Hello everyone, welcome to our today's webinar. I'm Vova, Head of Community at SmartCat, and we will be talking today about computational linguistics, the rise of the machines, and all this fun stuff. Today with us, actually our presenter, my co-host today is Michael White of the Ohio State University. Hi Michael.
Hi, good morning.
How are you? How's the weather?
It's a beautiful day here.
I see.
Getting some echo.
We are going to have these crowdcasts in a few channels on YouTube, on Facebook, on our community forum, and on Crowdcast. So the best way to watch it is to follow the Crowdcast link that is located under the video, because you can ask questions here, chat with other people, respond to the polls. So if you're already on Crowdcast, check out the questions to the left, ask your own, upvote the ones you like. You can also vote on the polls, which I created to understand the audience better. And that's it. Let me remind you that this whole show is brought to you by SmartCat, which makes people and technology friends with each other. And if you are not on SmartCat yet, you can follow the green button under the video and check it out. So, if everything is fine, Michael, tell us a few words about yourself and your area of research.
Sure. Is this okay? Too much of an echo?
I sometimes lose your video, but at least I do hear you.
Yeah, I'm losing an echo. It's okay. So I'm in the Department of Linguistics at the Ohio State University, but I've been working in computational linguistics for, I think, over 25 years. And in that time, the field has changed tremendously. So it used to be that when we teach an introductory course about natural language linguistics, most students know. We just say it's a kind of thing or Google Translate.
Sorry, Michael, to interrupt you. I think we're having some technical problems with you. Can you reconnect and see if it gets better after this?
Sure. Let me also headphones in case. So I'll read right.
Just a second, everyone. We will wait for Michael to reconnect. Hopefully, it will get better afterwards.
Okay, I'm back. Can you hear me?
I do hear you. What about you guys? Can you type in the chat if it's better now?
Let's see. That's better for me. Okay?
Yeah, I think it's better now. So, sorry. Okay, I lost your video once again, but
so
can you tell some?
Yeah,
I do hear you. So, can you repeat what you were telling about your background?
Yeah, I was just mentioning how much the field has changed in 25 years. I imagine some of your audience is aware of some changes. Certainly, the availability of fairly high translation is a big change from 25 years ago, reflecting in part the data-driven methods to deal with the complexity of language. At the same time, people like me or in the linguistics department study just how much remains to be done and just how amazing human language is and everything that's going on. My own particular research has been in, at the theoretical level, looking at natural language semantics, so really studying meaning and how it relates to syntax and language. And then on the applied side, I worked in the area of natural language generation, which is how if you go from data or to text, so rather than starting from text in a machine translation context from one language to another, starting with data. So as would happen in a lot of conversational agents that actually understand what they're talking about and just can't talk about a wide range of things. So depending on the task you're trying to solve, they're quite different methods might be relevant. And that these are issues that becoming more and more important, I would say, as AI technologies become more pervasive.
Sorry, yeah, because the sound keeps dropping sometimes, but I hope that we could make out most of it. Are you talking now? Because I don't hear you.
No, I'm not talking now.
Okay.
Is that
Sorry.
okay? Can you hear me?
Yeah, now I do hear you, but it keeps dropping sometimes. But
okay, I'll try to speak louder.
I think your video is out, but I do hear you right now.
So maybe I should start with this madly ambiguous, which is how we became aware of the work I was doing. So,
yeah, I can show the game to our audience by sharing my screen for a while, and then you will describe how you came up with that idea.
Sure.
Just 1 second. Not here. Okay, so here's the game that's called Madly Ambiguous that Michael and his colleagues wrote. Let me see if I can pop it out here. Oh, sorry, I will try once again. Yeah, should be better now. I focused on it. So the game is called Madly Ambiguous, and it studies how computers try to disambiguate sentences and meanings, right? Correct me if I'm wrong as I go along, Michael.
Yeah, that's right. So
by the way, now we can hear you quite well, so I guess you can describe it yourself, how you came up with it and what's the idea behind it.
Right. So I'm involved in a project that sponsored by the National Science Foundation here in the US. And the goal of the project is to develop ways to automatically paraphrase sentences which are ambiguous, to clarify which interpretation the computer has come up with. Now, as part of that project, one of the big goals of the National Science here is to promote understanding of science among the general public. So we actually developed this game for dual purpose of being able to use it as a science medium to explain a little bit about how ambiguous stuff for computers, and also to use it even in undergraduate instruction. People are just learning about language technology. So the game is designed to help people all the way from grade school kids to adults about structural ambiguity, right? So not just what the words mean, but how the words come together to make larger meaning, and how that can end up ambiguous. So what's on the screen now? It's spaghetti. So it's quite obvious to you and me that she would be using the fork. So the goal of the fork in the sense would be the utensil. It's what she's using to eat the spaghetti. But how do you know that she's not actually eating the fork, that it's not part of the dish, right? So in a sense, like Jane ate spaghetti with meatballs, it's the same. You've got a prepositional phrase with and then a noun phrase, meatballs. And there, that meatballs is part of the dish. So there are these two possible interpretations for it's totally obvious what is usually meant. But computers really don't know very much about the world, so how in the world are they going to figure out what people mean when things are ambiguous? And language turns out to be massively ambiguous, much more than we realized 25 years ago. And computers have to make their best guess, not in the same way that people do, or at least not today. They don't have the same experience of the world. So that's one of the main goals, just to explain that these kind of things are hard for computers because it's so obvious to people. So that's part of the game. Begins with an introduction. Actually use this at a museum when there's someone there to explain it. We often actually skip this whole introduction if there's someone just to explain it dynamically. So you could either skip back or skip to the end, and we can move on to the game part. So there's this introduction that describes the issue with structural ambiguity, and then there's the game part. So let's see if you go back to the first screen there.
The first one with
one more
with the
to the left. Yeah, and if you you got to scroll down. Oh no, skip instructions and at the top. I'm sorry. Yeah, go to the left.
Okay.
Go back.
Here?
Back.
Okay.
Maybe you have to do back one more.
Sorry.
There we go. So click skip instructions.
Okay, yes, I can click
it.
Oh no, I didn't realize that. Okay, skip instructions and play. Yeah.
There we go. So this is the game part. And what you do is you type a phrase in the box there, a noun phrase. And what the introduction has shown is that these phrases are actually ambiguous. So, okay, if you try Jane has to get a ketchup and hit enter. So that's Mr. Computer Head. He's a bit smart.
Fascinating.
So he comes back with the second interpretation, right? So that you use the ketchup to eat the spaghetti, that would be silly. He thinks the ketchup was part of the dish, had spaghetti and ketchup. So you see it's using this picture. This is Ajda's sister. Ajda was the one who programmed the interface and came up with a lot of ideas about how to do this. Right, so this was the correct interpretation. And he says something silly like piece of cake.
With a piece of cake, we can enter this as a noun phrase.
So you want to play again?
What's the difference between advanced mode and basic mode?
Well, let's do one more basic mode and then
okay.
Okay, so let's try President Trump here.
Trump?
Yeah.
With a Trump or with Trump?
Yeah.
Like this?
Yeah.
Okay, we're getting political here. Oh no.
Okay, so this is one of our known examples that Mr. Computer Head gets wrong. So Mr. Computer Head thinks Trump is a utensil like a fork. Right? So that's being shown. Interpretation is like the one where she's using the fork. If you scroll to the right, you'll see that there are other interpretations. And it's actually the fourth one there.
Yeah, sorry, I clicked it too quickly.
Yeah. So let's switch to advanced mode
now. Should I enter something?
Let's try President Trump again.
Okay. Yeah, now it's more smart, right?
Yeah, it's a bit smart.
So do you learn from my input, or is it the advanced mode?
Well, so let's go ahead and say yes. And you scroll down a little bit, or we can try more examples. I was going to say let's find out how it's done. Okay.
Let me try to make the window larger so we can see.
So Mr. Computer Head has two strategies which are supposed to be representative of the kinds of methods that are used today in computational linguistics to disambiguate what people mean. The first one is basically a classic rule-based or knowledge-based approach. In this first basic mode, he's really only paying attention to the main noun in the noun phrase. So if you say President Trump or Trump, it's just looking up Trump. So let's skip ahead here. And what he's using is WordNet, right? So it just uses a light analysis of the noun, right, to try to figure out the parts of speech of each word, the lexical categories of each word, in order to find the main noun. So, for example, fork here or trunk. Okay, keep going forward. Sometimes it's not obvious what the most informative noun is, and he gets it wrong sometimes. But the more interesting thing is, even when he gets the noun right, sometimes he'll get it wrong. Okay, so we go forward. Okay, so if you're not familiar with WordNet, that's a project developed over quite a number of years at Princeton University, where they've analyzed the meanings of a very large number of words, but it's not completely comprehensive. And they've grouped the different senses of words together with other related senses, like you would get in a thesaurus. But they also identify more general and more specific words. So if you go forward, we'll have to figure this. Oh, there we go. So WordNet arranges word meanings in a hierarchy in a way that is common to lots of knowledge-based approaches in artificial intelligence and computational linguistics, right? So you see that cheese is a dairy product, and along with meatballs and other kinds of dishes, those are kinds of foods or nutrients. Whereas spoons and forks are utensils, which are kinds of human-created artifacts. Both of those are physical entities, and so on. That's quite different from something like gusto or zest. So if you say, Jane ate spaghetti with gusto, that tells you about how she was really enthusiastic, for example. So the strategy that Mr. Computerhead uses in basic mode is to look up the word and then just see, well, what kind of thing are we talking about? Are we talking about a human-created artifact that could be used as a utensil? Are we talking about something that would make sense as a food or nutrient, something that would make sense as a feeling? And if not, let's just assume it's a person, because there's lots of names that it doesn't know about, so that's kind of it. So that tends to work pretty well. Even when people are trying to fool the Computerhead, he often gets, let's say, 75, 80%, right? The problem is that WordNet includes all the senses they could come up with for the words they analyzed, even fairly archaic or rare meanings. So I was surprised to find when we were going through this that Trump is a fairly archaic synonym for trumpet, right? Which is a kind of musical instrument, and therefore a kind of artifact. So it thinks Trump is a musical instrument, and Mr. Computerhead is creatively thinking you could be using something like a trumpet to eat the spaghetti, right? So that is not a meaning a person would come up with, because it's something rare.
Michael, sorry to interrupt you. Can you try reconnecting once again? Maybe it will, because it got worse again. Maybe it will get better.
Reconnect?
Yeah, I'm just to refresh the page.
Back to me, or can you hear me?
I do hear you, yeah, but sometimes I keep losing it. I'm not sure if it's the equipment or the network or something else, but...
Okay. So the good thing about an approach like this is you can actually understand what it's doing. So if you find it makes an error, like it did here with President Trump, you can just go and edit your knowledge base, right? So if you're setting up an application that's supposed to have a dialogue about a certain range of products or something, and you start with WordNet as a source of word meaning, you could discover for things that it gets wrong, oh, let's just delete this out of the knowledge base. That's knowledge that's unhelpful, right? And you can add stuff in. So the advantage is that it's completely transparent what's actually going wrong, and you can fix it if something goes wrong. The disadvantage, it doesn't have knowledge, it doesn't have knowledge of frequency and what's more likely. And that seems to be fundamental to how human language actually works. So it's possible in certain domains to get this kind of knowledge-based approach to work very well, but it's a lot of work and it doesn't take advantage of a range of possible clues that when people use language, they weigh a lot of competing interpretations and rapidly come up to the intended interpretation, in most cases, without so much trouble. So if we keep going to advanced mode, we can talk about a rather different approach to understand language. Yeah, so this is just explaining what I was saying about how it chooses its interpretation.
Yeah.
So if some of your listeners are familiar with the idea of word embedding, but this has had a remarkable influence on the field of language technology, along with deep learning just over the past few years. And the idea of word embeddings is to represent meanings in a multidimensional space. So you think, well, each word has a meaning in some space, and the goal is to put similar words in a similar point in the space, and to be able to do this automatically without hiring a bunch of people to develop knowledge bases. And this can be done just by looking at what kind of context words appear in. So words that appear in similar contexts probably have similar meanings. And we're using some data that Google's made available, trained on a gazillion words. I forget if it's a trillion or what, or 100 billion, some crazy amount. So you learn all kinds of things about what words mean just based on where they appear in context. But it doesn't mean that it, suddenly actually knows what a meatball is. It just has some idea of where this word should be in context. Okay, so if we go back to the explanation, I think we have a picture that might help. Right, so when you have a whole phrase, an ongoing topic is how do you figure out what the meaning of the phrase is as a different point in space based on the meaning of the word. And what often works much better than you might think is just averaging each word. Right? So if each word is a certain point in space, you take the midpoint of all the words in the phrase. You can put a little bit more weight on the more informative words to get a slightly better picture. But that's an approach that's often a baseline for a lot of state-of-the-art methods that are trying to understand language in a broad context. So for disambiguation, what we can do is compare that point in meaning space to the ones that we've already learned about. So
like
you can learn from some
fork and
yeah. So we have examples of phrases people used for food and ones they use for utensil and for people. So it can just use a kind of nearest neighbor method. So the phrase that we enter, like President Trump, is that more like the point in space that we got for other examples that were people, right? So this picture is showing a sample of different phrases and the categories that people told us were. So something like my good friend Joe would be a person, also might be someone you'd be eating your spaghetti with. My dog is another example that goes wrong in basic mode because dog is sometimes short for hot dog, right? So if you have spaghetti with a hot dog, that would mean one thing. But if you just say spaghetti with my dog, you probably mean your canine friend. So, the different, how likely different meanings of words are can be learned from data, and that can help with this disambiguation. So it's just seeing for the phrase you type in, for the point in meaning space that we come up with for the phrase, where does that cluster? Is it closer to things that we know are utensils or the company or food or what? So that's why President Trump, it will get right, because that ends up being more similar to different people that are different companions. But if you click on to the next slide, you'll see that this doesn't always work either. So if you see in the middle there a phrase like an Italian, so ate spaghetti with an Italian, ends up pretty close in meaning space to her Italian passion, right? But her Italian passion is more like gusto or zeal. Mm-hmm. It's a way of eating. But Italian, contributes its meaning to that phrase in a way that it comes up to be quite similar just to the phrase an Italian. So this kind of approach that just simply averages the meanings of words together can make these kind of mistakes where it's going to mistake her Italian passion as a person, or conversely an Italian as a way of eating things. So this is intended to show the kinds of things that work well, and that learning from data can get a lot of things right. All kinds of things that did not have to be anticipated by the designer, but things can still go wrong. And the frustrating thing is when they do go wrong, often it's very hard to figure out exactly why. So there's a lack of transparency. So unlike the rule-based method, where it's quite easy to fix problems that go wrong by fixing the underlying knowledge, in data-driven approaches, when things go wrong, you say, well, it's just how the numbers added up. We trained it on some data, and it gets something right, and it gets some things wrong. And these word embeddings are often the first step in today's deep learning approaches, like used Google's new neural machine translation. But they're just the first step. Things get even more complicated as it runs through the whole deep learning setup. And even though on average things are demonstrably better, when things go wrong, it can be very difficult to understand why. Does that make sense?
Yeah, speaking of neural networks, as you said, they are on a roll now, at least in the mesh and translation field. One of the things with them, I think, is that you cannot always understand how exactly they act. So unlike these methods that you talked about, the nearest neighbor and all this clustering stuff, if you put some information at the input of a neural network, you never know what happens inside to let it come up with some output.
Yeah, that's right. So this method of using the nearest neighbor is a new approach that's being used in neural networks to combine what are called memory-based approaches with kind of the standard, let's say, classification or generalization-based approaches. So can you learn from just a single example? This is sometimes called one-shot learning. So deep learning generally takes tons of data. You have to have a lot of data before it works very well. Whereas one-shot learning aims to learn from single examples, like people often do. And that can work if you're building on what you've learned from a lot of examples to begin with. So if you have a system that already has a good way to represent the meaning of phrases, then you're in a better position to use this kind of memory-based approach, the nearest neighbor approach of learning from single examples. So these kind of methods are being used in combination now. So the memory-based approaches are a little bit easier to understand, but they still lack the transparency of traditional rule-based that you can't just go and fix the knowledge. So that's one of the things I'm very interested in moving forward is can we combine the best of the traditional rule-based approach with the kinds of robustness of data-driven trainability you get from neural net methods to have systems that we can actually understand what they're doing, or at least in part, enough to be able to fix them.
How are people involved in this whole endeavor? Because you talked about computers learning from the inputs we provide to them. So in your game, for instance, does your game get smarter over time as more people use it? And
right. So for example, in advanced mode, it can get smarter if we take that data that's being collected when people type in their examples and retrain the system. So, it's taking the meaning of each kind of expression as essentially an average of all the phrases that have been told where utensils. examples, and all the ones he was told were manners, ways of eating, and so on. It actually makes clusters those into smaller groups. So it's a bit of a compromise between the single closest example and a number of examples that seem to be similar. But the more data it gathers, and in principle, the better it should get, because it'll have seen almost everything people can come up with at a certain point. So that trainability is one of the strongest selling points for data-driven methods.
Do you think that inside these neural networks there can exist some actual kind of primitive conscience, because there are neurons and there is some information fed, some training undergoing? Do you think it is possible that some flatworm type of conscience develops inside there?
That's a fascinating question. I don't think it will happen without it being explicitly designed into the system. Right? So the system would have to have some model of its own internal workings. This is a topic that I find very interesting, and I've been doing some reading on the nature of consciousness. There are theories, but there's certainly not clear understanding of how it works in people. I'm not the kind of person who's afraid of AI suddenly taking on some kind of consciousness and refusing to open the bay doors or whatever it was that Hal did. So I think, though, as we move forward, conversational technologies, having a better model of the participants in a conversation, and where the computer itself fits in the conversation. So having that model of itself, which is similar to its model of others, may produce something like consciousness. But yeah, I'd be interested to hear what other people think about that, because I don't have a firm opinion.
Yeah, the reason I ask, a lot of reasons to ask this, of course, but I remember this experiment by Facebook, who tried to train chatbots to communicate with each other, and they ended up devising some kind of language that a human could not understand, and it caused a lot of eerie reaction from the audience, maybe not from everyone, but anyway, it looked on the verge of funny and eerie. So how does such thing happens? Is it because there is no trainer involved, or do you have an idea of how this would happen?
So there are two issues there. So the interesting thing is that using a kind of learning that's reward-based, so not just, what's the right interpretation here? Is it manner? Is it instrument? But just we want to reward behaviors that lead to desired outcomes. Like, did we get the task done? They were involved in a negotiation setting there. So training the system to reward certain behaviors can lead to behaviors which become more efficient over time. So my understanding was that the two computational agents that were conversing moved towards a more efficient form of language, which was no longer understandable to people. Now, that kind of thing happens all the time in human conversation. So a prominent theory of understanding by the psycholinguists Martin Pickering and Simon Garrett at the University of Edinburgh and Glasgow University is all about how people's interpretations come into alignment. So this can be at the low level. The way people pronounce words can become more similar over time, especially how people describe objects that are things they've never seen before. You might start off with very lengthy, awkward ways of describing things, but over time they come up with very efficient ways to describe these things. And in general, people rapidly learn to adjust their communication to make it more efficient. Now, with people, even if you have a very efficient way to refer to some crazy looking object, if suddenly you're talking to someone new who hasn't been part of the conversation all the time, you're going to describe it in a more elaborate, standard way not the shorthand way, to bring them up to speed, right? So people, to a certain extent, can keep track of what the people they're talking to actually understand it and know. So that was the problem in that experiment, is they couldn't suddenly switch models for a different interlocutor, for a different conversational partner, to use language that they would understand. So being able to adapt your language is really fundamental to human conversation, but also being able to have some kind of model of your conversational partner. That's the part that was missing there. Now, whether there was consciousness, I don't think it shows any evidence of consciousness.
No,
self-aware.
But it causes some spooky feeling of it might being there, but yeah, might be not real consciousness. Anyway, speaking of this adaptability, could it be an idea for research, and is it already maybe something that is researched in computational linguistics, to make computers adapt certain texts to a certain audience? For instance, you get a description of the general theory of relativity, and then you say, explain it to me as if I were a 5th grader, for instance. And then it uses a neural network to adapt all the words and to bring shorter sentences and so on. Is it possible?
Yeah, in fact, that's a quite active area of research. There's a whole subfield of intelligent tutoring systems that, to a certain extent, are adaptable to certain levels of understanding, right? So they know kind of what grade level. Generally, they may not be able to switch infinitely from an infant all the way up to an expert, but at least to some extent can adapt, not only to a general level, but also kind of the specifics that have already been understood. And then there's another fairly active field, people working on text simplification, which is also related to summarization. A fairly complex text, and express it for children or people who are just learning a language. You really have to simplify both the words and the syntax, how the words are put together, to make it more understandable. And that is not something you want to do for everyone. So for an expert to express it with a lot of short, simple sentences would be tedious. It's like, get to the point. I can handle a greater level of information density. And in fact, the idea of information density is one of the exciting ideas in psycholinguistics, again, on what makes human communication efficient. And we find we're always striking a balance between expressing things clearly and expressing things efficiently. But that really depends on who you're talking to. And that's one of the major failings of current technology, but things that people have done some research on, and it's an active area going forward.
It reminds me also on this dilemma or conundrum in informatics, that you can have a code either run quickly or use data efficiently. So it's either big or it's slow. So it's some kind of uncertainty principle in informatics. Is it something like this in linguistics, that you can either explain something short or with less information density, then it becomes more clear to the listener, something like this?
I think that's a related issue. I don't think it's exactly the same, because the role of the conversational partner and what their general understanding is, and what they know specifically, also what their preferences are. So I've done some work in dialogue systems on trying to describe products and services relative to what people really care about. So contrasting the good and bad of different options, but the things that they care about, not things that other people might care about. So that,
yeah, it's fun to think of the future when you can.
Yeah.
Sorry for interrupting. When you can just plug into any online manual and enter like, I'm an engineer, or I'm a marketing specialist, and or maybe it will even understand the level of your knowledge and the direction of your knowledge by analyzing the websites you visit, and it would adapt any text on the web to your personal profile.
Yeah. So I would say that systems that are using the more traditional knowledge-based approach have shown quite a range of adaptivity and ability to tailor information, but often in a way. So if we're just talking about physics or electronic circuits or something that we're teaching people about, we can do this kind of adaptation. But if we're talking about taking any web page and adapting it for an engineer versus a child or something, that's much harder, and that's an active area of research, but it's very hard. So kind of simplifying it to different grade levels, maybe not too far from, but from really specific knowledge of different kinds of people might have, or specific people would have in the general case. So with any language, it's just a much harder problem. So that would be like it's an advanced mode, but now doing simplification.
Because in translation, one of the dilemmas in translation is that you often have source text that is suboptimal, and there is always the question whether you should try to improve it when you translate, or whether you should just keep it with I don't know, sentence with 100 words with a lot of subordinate clauses and so on. So having such a simplification tool can also do great things in the translation industry as well, I think so. So it's something people might think about. Another thing I wanted to ask is that you were talking about information density, and it seems to me, I talked to a lot of translators, that sometimes, for instance, in English, it is much easier to express certain things than in other languages. I don't know, speaking of manuals and speaking of some instructions, usually English makes it pretty easy to explain, and when you're trying to translate it, I don't know, to Russian or to Arabic, it suddenly turns a very complex task. So what does actually affect a language's ability to be used for simple explanations? What does it depend on?
Well, I would say, fundamentally, you need to have the words and the lexical concepts that have been found to be useful to describe certain things. So I would say a lot of that is simply a function of more time having gone into describing certain technologies, and over time, the words to use to do that become optimized. So I doubt that's inherent to English, the historical accident of which language was used first and for the longest time for some of things. Certain aspects of English, English is very flexible with things like noun-noun concept. So you can string a few nouns together to mean a very specific concept. And that's a very efficient one, very short, compact phrase. That can be rife with ambiguity. So in general, you put several nouns together, and there's a crazy range of things that could mean. And it might be real trouble for a computer trying to understand it. But for people, if that's referring to some kind of concept, if it's having to do with computers or some kind of medical terminology, in a specialized area, it'll be clear to everyone and very efficient to have that kind of thing. So there's certain aspects of English maybe which are advantageous, but I think it's mainly that so much power is in the words themselves and the phrases and specialized phrases that people learn to use. That's a big leg up there. What do you think? I don't work in translation. I'd be curious what you.
Yeah, I've been thinking about this for a long time. Yeah, English has very short words for one. I even sometimes play a game with myself by putting two consonants and one vowel in the middle and trying to think if it is a word in English, and most often it is a word. So you put teen or kid or walk or anything else, it happens to be a word. So it uses letters very economically inside the word. At the same time, it uses a lot of words. For example, when you compare Russian to English, in English you have words that are like 25% shorter, but at the same time there are 25% more words. So you have, instead of having, maybe if you compare to Russian, where every word is a huge construct that you need to somehow fit to some other construct, in English every word is like a Lego piece that is really small, and when you put them together you can build anything you want. That's what was my impression.
Interesting. Yeah, one of the things I try to emphasize in my undergraduate teaching is this trade-off between between ambiguity and efficiency. And that's actually been fairly clearly demonstrated with and word lengths. So you see that in English, the short word or the easy words, the ones that are easy to pronounce, these things go together. They're the ones that get extra meanings piled up on them, right? So for example, the word run in English could mean just the activity, like a fast jog or a fast walk, but it's also has a specialized meaning in the baseball. It means to score, you know, like a goal in soccer, but it's a run in baseball. Or, you know, there's other specialized meanings.
Run a company.
Yeah. So these meanings get piled on to these short words because it's efficient. And it's because people in different contexts can rapidly figure out which meaning you mean. So it's not confusing for people to use the same word in so many different ways. And that kind of pressure towards efficiency over time can make the language very, very efficient. So, but it has to be most of the time easy for people to tell what you mean and rapidly to figure out what you mean.
Yeah, that's also what I thought.
Towards clarity, but also pressure towards efficiency that leads over time to this kind of optimization. But that's for people, right? So people have these big brains, and we can rapidly do inference and figure out what people probably mean, based in part on what we know about the world. Computers can't do that. You know, maybe with robots, they'll have more direct experience with the world. But right now, that's the problem. Computers have to guess what you might mean for these words that can mean all different things, and they can't do it nearly as well as people. So that's the fundamental source of the mismatch between language technology and how humans use language.
Yeah, and a perfect language for computers would be where there is no synonyms or homonyms at all. So where there are no words with ambiguous meanings.
Yeah, but that would be easy for computers because they can rapidly transmit megabytes or gigabytes of information. So the amount of information that we can convey in speech is very limited. It's only a few bits per second. So we have to really rely on the smarts of the people who are talking to fill in all the blanks.
Yeah, but you know, in terms of globalization and in terms of bringing the same amount of information to the maximum amount of people, I remember this initiative. I don't know if it's alive right now. It was called Unified Networking Language. I think it was developed under the auspices of the United Nations. And the idea was that instead of writing documents in a human language, you write them in a tree-like form, where on each branch you have something like WordNet entry or something like this. And so there would be trained people who would write documents like United Nations documents in this language, and these would be very easily transformable into any language in the world if you have the rules set for this language.
Yeah, so I know those as kind of controlled languages generally, and that can be effective, but it's not natural. So people have to learn how to do this, and it's not necessarily obvious. So if it's worth the effort to train people to do this, so it can certainly work in specialized domains. You know, I understand that for aircraft manuals, it's worth the effort. But one of the advantages of human language for interacting with computers is it's natural for people. It doesn't require instruction and training. It's just how we normally communicate. So people are very adaptable, and if it's worth it to get the people to adapt and train them, that can be effective solutions sometimes. But in the longer term, researchers we're working on trying to get computers to do the adaptation and make them work the way people do with language. But it's hard because the way human language works, how it relies so much on inference and shared understanding and knowledge and adaptation that we're talking to.
What's the next big thing in computational linguistics? Because we as translators, we have seen the rise of neural machine translation. It really feels like an explosion in performance, not performance, but quality. So it feels like it's really the big thing happening right now. So maybe you have some even bigger things somewhere deep in your research labs. What would that be?
Well, it's exciting because what people did 25 years ago, when there wasn't massive data deep learning, they actually tried to more carefully model how we think people work. And people don't just use knowledge of the world, but they use knowledge of how people act in the world. So what kinds of goals and plans do people have? What it is that people are really trying to do. And when people interact, they actually don't just answer questions. Literally, they try to actually answer in a way that's helpful for what your real purpose is and figuring out what your real purpose is. So that kind of work fell by the wayside when it became hard to scale. But people are starting to think about interpretation and context in terms of what the goals and plans people really have, as well as how things fit with the context, right? So part of what makes language efficient is not having to restate things that should be obvious from the context, and doing a better job of taking the context into account is actually something that these new neural network models make possible. So there are new ways to think about computer interpretation of language more like human interpretation in a way that actually will probably work in the general case. So to give you an example, even today with Google's new neural translation, it's still to be working entirely on a sentence basis, right? So if you have a language like Spanish, which is pro-drop, meaning that you can, instead of expressing a referent pronoun, you just don't say anything, right? So in English, you might say, Mary has a dog, she also has a cat. And we have to say she to refer back to Mary, right? But in Spanish, you would say Mary or Maria has a dog. You say it in Spanish, Daniel go. And then in the next sentence, rather than he, you'd say also has a cat, and you don't say she. So you plug this into Google Translate right now, and the equivalent of Mary has a dog, he also has a cat. So it's smart enough to realize that if you're translating from Spanish to English, you have to put a subject in there. You can't just leave out the subject in English. You have to put something in. But it really has no idea what to put in, and it guesses instead of right? Because it's not taking that context into account. But there's been research over the past couple of years where people are starting to take context into account, and there's ways to do that with neural network models that I expect to see very soon. Whereas actually taking into account what the goals and intentions people have is a more challenging long-term problem. So at least people are thinking about that again, and neural network models may make it possible to actually do that in a way that works in general and not just in these very limited applications. That's harder to say how long that will take.
Yeah, okay, we can only wait and see, I guess. Anyway, I think we will be wrapping it up, and thanks, Michael, for this insightful conversation. I'm sorry that the quality was not always very good because some guys experienced sound problems. Perhaps it will be better in the recording, which will be available at the same link afterwards. Okay. And thanks once again. We did not, maybe we posed more questions than you answered, but I think it's good to have some new topics to think about and maybe to come up with something great.
Okay. Well, that was a pleasure for me as well. Thank you for inviting me.
Thank you, and I hope to see you again sometime. So drop by to everyone. Thank you for coming, and come back every Thursday usually. Stop by our Crowdcast channel to see if we have any new webinars. We are going to cover many insightful, exciting topics in the future, and see you next time. Thanks, and bye-bye.
Okay, good luck with that.
Thanks, bye.
Bye.